Morning, students. I'm Ravina. Today, I'm here to discuss some topic about the control system. That is, what are the types of feedback control system. Last class, we have discussed about effect of feedback on stability, gain, and noise or disturbance of the control system. So, I think you might have gone through that video, and you should have understand the concepts in effect of feedback on various parameters such as gain, stability, and noise or disturbances in a control system. So next we will go to the topic types of feedback control systems. So feedback control systems may be classified in a number of ways depending on the purpose of the classification. According to the method of analysis and design, control systems are classified as linear and nonlinear control systems, time varying or time invariant control systems. And these two classification is purely based on the method of analysis and design. And there is another classification that is according to the type of signals used in the system. The control systems based on control system classification based on the type of signals used in the system is continuous data control systems and discrete data control systems. And this system is also called modulated control systems or unmodulated control systems. Also, there is another classification according to the main purpose of the system, that is position control system and velocity control system. And these systems controls the output variables such as position or velocity. This is the types of control system classification. Next we will go to each topic. Okay, first is linear versus non-linear control systems. And this classification is based according to the method of analysis and design. Linear systems do not exist in practice. All physical systems are non-linear to some extent. That is the point. That means linear systems do not exist in practice, and all or most of the physical systems are non-linear to some extent. So, linear systems. These systems are idealized models fabricated by the analyst purely for the simplicity of analysis and design. When the magnitude of the signals in a control systems are limited to some ranges in which system components exhibit linear behavior, then the system is essentially a linear system. Okay. In the case of a linear system, the signals that we are going to apply for the linear system is in a limited range so that the system components exhibit linear behavior. So the system will be a linear system. So we can say that the mathematical model of a system obeys the principle of superposition. Then the system is called a linear system. In the case of linear system, that system will obey the principle of superposition. Then there is a question, what is principle of superposition? I think you might have studied it in signals and system topics. For a system to be linear, it should obey principle of superposition. Then the principle of superposition states that the response produced by the simultaneous application of two different input is the sum of two individual responses. Again, the principle of superposition states that the response produced by the simultaneous application of two different input is the sum of two individual responses. Suppose we have a system and we are giving an input A into R of t, then it will produce B into C of t. Also, we are giving another input U into V of t, and that will give an output X into Y of t. Then we can state superposition principle as the response to the linear combination of A into R of t plus U into V of t gives a linear combination of the individual output, that is B into C of t plus X into Y of t. Then the system is called a linear system. This principle is called a superposition principle. Okay, you got the idea? That means if the system has a response B into C of t for an input A into R of t, and system has a response X into Y of t for the input U into V of t, then the system responds to the linear combination of these two inputs, that is A into R of t plus u into v of t, that is the linear combination of these two inputs, and the system response to the linear combination of these two inputs gives a linear combination of the individual output, that is v into c of t plus x into y of t. This principle is called the superposition principle. So for a system to be linear, it should obey principle of superposition, and the system components will behave as linear for a range of inputs. So next is the nonlinear systems. When the magnitude of the signals are extended beyond the range of linear operation, the system component exhibit nonlinear behavior. Examples for nonlinear systems are the amplifiers used in the control systems often exhibit a saturation effect when their input signals become very large. We know that amplifiers will work in the saturation region. In the saturation region, there is no linear relationship between voltage and current. So, amplifiers used in the control systems often exhibit a saturation effect when their input signals become very large. Also, the nonlinear spring characteristics and nonlinear friction force or torque between moving members, etc., are examples for nonlinear systems. So, we can say that when the magnitude of the signals are extended beyond the range of linear operation, the system components exhibit nonlinear behavior. And linear, we know that we can say that linear systems are easy to treat mathematically, but nonlinear systems are difficult to treat mathematically. So in the design of a control system, first we will design the controller based on the linear system model by neglecting the nonlinearities of the system. The designed controller is then applied to the nonlinear system model for evaluation or redesign by computer simulation. So we will not directly design a nonlinear system. First we will design the controller for a linear system so that it will behave linearly, and then this controller is then applied to the nonlinear system model for evaluation, and then it is redesigned by computer simulation. That is process that is behind the system design, nonlinear system design. Okay, next we will discuss about time varying and time invariant systems. What is a time invariant system? From the term itself, time invariant, we can say that when the parameters of a control systems are stationary with respect to the time during the operation of the system, then the system is called a time invariant system. From the term time invariant, we know that the parameters of the control systems are stationary with respect to the time during the operation of the system. A control system can be represented by mathematical equations by applying appropriate physical laws like KCL, KVL, Newton's law, etc. The mathematical model of a system is characterized by differential equation. Usually we are representing the control system by mathematical equations, and that mathematical equations is obtained by applying KCL or KVL or Newton's law, etc. And these mathematical equations are later used for analytical purposes. A time varying system without a nonlinearity is called a linear systems. Such systems are called linear time invariant systems. If a time invariant system is linear, then such systems are called linear time invariant systems or LTI systems. If we are writing the equation for a linear time invariant systems, then in that case the coefficients of the differential equations that represent the systems are constants. Okay, in the case of linear time invariant systems, if you are writing the differential equation corresponding to that system, then the coefficients of the differential equation that represent the system will be constants. Next is time varying system. When the parameters of a control systems or the elements of a control systems that vary with the time, then that system is called a time varying system. That means in the case of time varying system, the parameters of the control systems or elements of the control system will vary with time. So that is called a time varying systems. Examples for time varying systems are the winding resistance of an electric motor is an example for time varying system, because in the case of motor, the winding resistance will vary when the motor is first being excited and its temperature is rising. Okay, so it is a time varying system. Also, guided missile control system is another example for a time varying system, because in that missile the mass of the missile decreases as the fuel on board is being consumed during flight. So it is an example for a time varying system. A time varying system without a nonlinearity is a linear system. Okay, a time varying system without a nonlinearity is a linear system. So it is called a linear time variant system. And if we are representing this system with a mathematical equation such as differential equation, then in the case of time variant system, the coefficients of the differential equations of the mathematical model will vary with the time. The analysis and design of the linear time varying systems are very complex than that of the linear time invariant systems. Okay. Next is another classification, that is continuous data control system, that is based on, this classification is based on the input signal. So we can define in continuous data control systems, so the signals at various parts of the systems are all functions of the continuous time variable t. In all continuous data control systems, the signals may be classified as AC or DC. And the continuous data control systems can be divided into two classification, divided into two, that is AC control systems and DC control systems. The classification of continuous data control system is AC control system and DC control system. In AC control system, the signals in the systems are modulated by some form of modulation scheme. In DC control systems, the signals are unmodulated, but they are still AC signals according to the conventional definition. Okay. That means AC control system uses some type of modulation scheme, but DC does not use any modulation scheme. But the signals used in AC control system and DC control systems are AC signals itself. Okay, you got the idea? AC control systems are used extensively in aircraft and missile control systems, because in those systems the noise and disturbances often create a problem. Since AC control system uses modulated signal, then the system will be less susceptible to noise frequency. Missile systems and aircraft system uses AC control system, because in AC control system modulation technique is using when we are modulating a signal with a carrier signal whose frequency is very high, and the signal frequency will be high, so that will be less susceptible to noise, less susceptible to low frequency noise. So these systems are using AC control systems. Next classification is discrete data control system. This type of control system differs from the continuous data control system in such a manner that in this, the signal at one or more points of the system are in the form of either a pulse train or a digital code. In the case of continuous data control system, we are using signals that are continuous with the time. In discrete data control systems differ from the continuous data control systems. In this, the signals at one or more points of the systems are in the form of either a pulse train or digital code. Discrete data control systems can be classified into sampled data control systems and digital control systems. In sampled data control systems, the signals are in the form of pulse data. In this case, the system receives data or information at a specific instance of time. In sampled data control system, the signals are in the form of pulse data, and in this case the system receives the data or information at a specific instance of time. And there is another classification, that is digital control system. In digital control systems uses digital computer or controller in the system, so the signals are digitally coded such as in the binary code. These all are the classification about the feedback or closed loop control system, and you can explain it with some examples. I think it is better to give assignment on that topic, because it is purely a theoretical topic. So we can discuss problems and all in the class, and you should write an assignment on explain continuous data control system and discrete data control system with examples. Okay, I will tell you the details about it in next session. So next we will go to Laplace transform, because Laplace transform is Laplace transform is used to solve differential equation. Usually we are representing the system or control systems by using differential equation, and it is easy to analyze a system by differential equation. So Laplace transform help to solve differential equation in an easy manner. Actually, what do you mean by Laplace transform? Suppose you are given a function f of t, Laplace transform of f of t is given by capital F of s, that is equal to integral 0 to infinity f of t into e raised to minus st into dt. That is the Laplace transform equation that you should by heart. Okay. Suppose you are given a real function f of t, then the Laplace transform of f of t is given by integral 0 to infinity f of t into e raised to minus st into dt. That means in the case of Laplace transform, we are converting the t domain signal into s domain. Okay, what do you mean by s domain? S domain contains a s plane that contains a real values and imaginary values. A time domain function is transformed into s plane. Okay. To understand the Laplace transform concept, we are next going to solve a time domain function. We are now going to convert a time domain function to s domain. So you are asked to find out the Laplace transform of a function f of t, which is a unity step function. So f of t is equal to u of t for t greater than 0, equal to 0 for t less than 0. You know that what you mean by unity step function. Unity step function will have a value of 1 for t greater than 1 and a value of 0 for t less than 1. So it will be like a step. That is why it is called a step function. Okay. You are asked to find out the Laplace transform of unity step function. Okay. So what is the first step? First you should write the equation for Laplace transform f of s is equal to integral 0 to infinity f of t into e raised to minus st into dt. That is the equation for Laplace transform. Next you have to substitute for f of t. You know that f of t is equal to 1 for t greater than 0 and it will be equal to 0 for t less than 0. Actually, in the case of finding Laplace transform, we are not interested in values which belongs to the intervals t less than 0. So we can neglect that values. So we can write integral 0 to infinity. Instead of u of t, we can write 1. Okay, 1 into e raised to minus st into dt. And in the next step, we have to find out the integral of e raised to minus st. What is the integration of e raised to x? Integration of e raised to x is x itself. What is the integration of e raised to minus st? Integration of minus st will be equal to minus 1 by s. That is within the limit 0 to infinity. So minus 1 by s and e raised to minus st with the limit of 0 to infinity. So we can substitute the values of infinity, which will be equal to minus 1 by s into 1 by infinity minus 1 by 1. That will be equal to 1 by infinity equal to 0. So that will be equal to 1 by s. Therefore, Laplace transformation of unity step function will be equal to 1 by s. Okay. That is the solution of Laplace transform for unity step function. Next, you are given another function f of t equal to e raised to minus alpha t. I think it is not clear in this slide. So I will read the question. F of t is equal to e raised to minus alpha t for t greater than or equal to 0. Find the Laplace transform where alpha is a real constant. The function is e raised to minus alpha t. You have to find out the Laplace transform of e raised to minus alpha t. So in the first step, you should write the equation for Laplace transform f of x is equal to integral 0 to infinity f of t into e raised to minus st into dt. Next, you should substitute for f of t. What is f of t? F of t is e raised to minus alpha t. So f of s is equal to integral 0 to infinity e raised to minus alpha t into e raised to minus st into dt. Here there are two exponential functions, that is e raised to minus alpha t and e raised to minus st. So we can combine it to one term, that is equal to integral 0 to infinity e raised to minus of s plus alpha into t. Okay, right? Minus is taken outside, t is also taken outside, then there will be s plus alpha into dt. So what is the integral of e raised to minus of s plus alpha into t? E raised to x has an integral e raised to x itself. But here instead of x it is minus of s plus alpha. So you can write it as the integral as that is equal to minus 1 by s plus alpha into e raised to minus of s plus alpha into t with a limit of 0 to infinity. The next step, you have to substitute the value of alpha and 0 for s. Okay, sorry, 0 for t. Okay, so minus 1 by s plus alpha into, if you are substituting infinity for t, e raised to minus infinity will be equal to 0 and e raised to 0 will be equal to 1. So you will get the question answer as 1 by s plus alpha, that is Laplace transformation of e raised to minus alpha t equal to 1 by s plus alpha. Similarly, you can solve all other equations, all other functions for getting Laplace transform. Actually, we are not interested in the detailed study of Laplace transform, but we should aware what is Laplace transform. And next, I will give you some important theorems in Laplace transform that you should remember. Laplace transform of k into f of t is equal to, k is a constant, so that will be k into Laplace transform of f of s, where f of s is the Laplace transform of f of t. And next, Laplace transform of f1 of a plus or minus f2 of a equal to f1 of s plus f2 of s, that is individual Laplace transform. You are given two functions, then Laplace transform of sum of these two functions will be equal to individual Laplace transform, summation of individual Laplace transform. Then Laplace transform of d by dt of f of t, derivative of a function. Laplace transform of derivative of a function is equal to s into f of s minus limit t tends to 0 f of 0. That is, Laplace transform of derivative of f of t will be equal to s into f of s minus f of 0. That means s into Laplace transformation of f of t minus f of 0, that is function at t tends to 0. Similarly, Laplace transformation of d raised to n f of t divided by dt raised to n equal to s raised to n into f of s minus s raised to n minus 1 into f of 0 minus s raised to n minus 2 into f dash of 0, etc. up to f raised to n minus 1 of 0. Next is Laplace transformation of integral 0 to t f of t into dt equal to f of s divided by s, that is Laplace transformation of an integral function will be equal to f of s divided by s. Similarly, if there is n term integral, then Laplace transform of integral 0 to t 1, integral 0 to t2, etc. up to integral t raised to n f of tau into d tau dt1 dt2, etc. up to dtn minus 1 will be equal to f of s divided by s raised to n. Next is fifth law, Laplace transformation of f of t minus tau into u of t minus tau will be equal to e raised to minus tau s into f of s. Next is limit t tends to 0 f of t is equal to limit s tends to infinity s into f of s, that is initial value theorem. Limit t tends to infinity f of t is equal to limit s tends to 0 s into f of s, that is final value theorem. Laplace transformation of e raised to minus or plus alpha t into f of t is equal to f of s plus or minus alpha. Next, Laplace transform pairs. You are given f of t and corresponding Laplace transforms are Laplace transform of unit impulse function del of t is equal to 1. Laplace transformation of unit step function u of t is equal to 1 by s. Laplace transformation of t is equal to 1 by s square. Laplace transformation of t raised to n is equal to n factorial divided by s raised to n plus 1. Here in this n factorial is not marked, so you should remember Laplace transformation of t raised to n is equal to n factorial divided by s raised to n plus 1. E raised to minus at, Laplace transform is 1 by s plus a. Laplace transform of t into e raised to minus at, Laplace transform will be 1 by s plus a whole square. T raised to n into e raised to minus at is a function, then Laplace transform will be equal to n factorial divided by s plus a whole raised to n plus 1. Sin omega t Laplace transform will be equal to omega by s square plus omega square. Cos omega t Laplace transform is s by s square plus omega square. E raised to minus at into sin omega t Laplace transform will be omega divided by s plus a whole square plus omega square. E raised to minus at into cos omega t Laplace transform will be s plus a divided by s plus a whole square plus omega square. Next topic is inverse Laplace transform. That means you are given the Laplace transform f of s, then the inverse Laplace transform will give the original function, time domain function f of t. Therefore, you can write f of t equal to L inverse of f of s. So the equation will be f of t equal to n by 2 pi j into integral c minus alpha j infinity to c plus j infinity into f of s into e raised to st into ds, where c is a real constant. And next we will go to the details of how f of s can be solved to get time domain function f of t. So if the Laplace transform function f of s is in the form q of s by p of s, that is a rational function, the partial fraction, that is in the p by q form, then the partial fraction expansion method can be used to solve for f of t. For that we are considering an example. G of s is equal to 5s plus 3 divided by s plus 1 into s plus 2 into s plus 3. To find out the inverse Laplace transform, the steps are, first we have to write g of s is equal to the partial fraction expansion method is explained here. G of s is equal to, here we can write it as k minus 1 divided by s plus 1 plus k minus 2 divided by s plus 2 plus k at minus 3 divided by s plus 3. The coefficients k minus 1, k minus 2, k minus 3 can be determined as k minus 1 equal to, how can you get the k minus 1? That is equal to, the denominator part of k minus 1 contains s plus 1. So k minus 1 will be equal to s plus 1 into g of s at s is equal to minus 1. So k minus 1 will be equal to, we can substitute for g of s. So s plus 1 and s plus 1 will be cancelled from numerator and denominator side. So k minus 1 equal to 5s plus 3 divided by s plus 2 into s plus 3. At s is equal to minus 1, we can substitute the value of s is equal to minus 1. So we will get k minus 1 equal to minus 1. Similarly, k minus 2 can be obtained by, denominator part of k minus 2 contains s plus 2. So k minus 2 will be equal to s plus 2 into g of s at s is equal to minus 2. Substitute for g of s and s plus 2 terms will be cancelled from numerator and denominator side. So k minus 2 equal to 5s plus 3 divided by s plus 1 into s plus 3 at s is equal to minus 2. We can directly substitute the value of s and we will get k minus 2 will be equal to 7. Next we have to find out k minus 3. For that k minus 3 will be equal to, the denominator of k minus 3 is s plus 3. So k minus 3 is equal to s plus 3 into g of s at s is equal to minus 3. Then substitute for g of s, and in the g of s plus 3 from the numerator and denominator side will be cancelled. So we will get 5s plus 3 divided by s plus 1 and s plus 2, and in that substitute s is equal to minus 3. So we will get k minus 3 equal to minus 6. So we obtain the values of k minus 1, k minus 2 and k minus 3. So we can rewrite g of s as minus 1 by s plus 1 plus 7 by s plus 2 plus minus 6 by s plus 3. And this is g of s Laplace transform. And to find out the inverse Laplace transform, we can easily find out the inverse Laplace transform of minus 1 by s plus 1 and 7 by s plus 2 and minus 6 by s plus 3. So inverse Laplace transform of g of s is equal to g of t, that is equal to minus 1 into e raised to minus t plus 7 into e raised to minus 2t plus minus 6 into e raised to minus 3t. here the answer is given in terms of u of t. It is similar to that of minus e raised to minus t plus 7 e raised to minus 2t plus minus 6 e raised to minus 3t. This is the solution. And next is another question. You are given g of s is equal to 1 by s into s plus 1 all raised to 3 into s plus 2. Find the inverse Laplace transform. Here we can write g of s is equal to k0 by s plus k minus 2 by s plus 2 plus a1 by s plus 1 plus a2 by s plus 1 whole square plus a3 by s plus 1 all raised to 3. This is equation, and here the coefficients corresponding to simple poles are k0 equal to s into g of s at s is equal to 0. That is the value of k0. Okay, therefore k0 will be equal to 1 by 2. We can substitute for g of s and cancelling the common term and substitute for s, we will get the value of k0 as 1 by 2. Similarly, k minus 2. What is k minus 2? K minus 2 is equal to s plus 2 into g of s at s is equal to minus 2. Substitute for g of s, so that s plus 2 and s plus 2 cancelled from the numerator and denominator side, and substitute the value of s is equal to minus 2, and we will get k minus 2 equal to 1 by 2. Next, these are the first order poles. Next, coefficients corresponding to third order poles are a1, a2, a3. So a3 equal to s plus 1 all raised to 3 into g of s at s is equal to minus 1. So s plus 1 all cube will be cancelled, and we can substitute the value of s as minus 1. So we will get a3 equal to minus 1, and a2 equal to, a2 can be found out by the equation d by ds of s plus 1 all cube into g of s at s is equal to minus 1. S plus 1 all g of, when we are substituting g of s plus 1 all cube will be cancelled out, and then we have to find out d by ds of 1 by s into s plus 2 at s is equal to minus 1. So when we are differentiating the 1 by s into s plus 2, we will get s into s plus 2 minus 2s minus 2 divided by s square into s plus 2 whole square at s is equal to minus 1. When we are substituting the values of s is equal to minus 1, we will get a 0. Similarly, a1 can be found out by d square 1 by 2 factorial into d square by ds square into s plus 1 all cube into g of s at s is equal to minus 1. If we are substituting, and if we are first, we will take the first differential such that 1 by 2 fact is equal to 1 by 2 factorial into d by ds of d square by ds square into 1 by s plus s into s plus 2 at s is equal to minus 1. First, when we are taking first differential, we will get the equation as shown in the slide, and then we can take the second differential equation, the second differential, and we can substitute the value of s, so that we will get a1 equal to minus 1, a1 equal to minus 1. So we can substitute for g of s. G of s is equal to 1 by 2s plus 1 by 2 into s plus 2 minus 1 by s plus 1 minus 1 by s plus 3 s plus 1 whole cube. G of t can be easily found out by taking the inverse Laplace transform of each and every term. That is equal to g of t is equal to L inverse of g of s, that is equal to 1 by 2 plus 1 by 2 into e raised to minus 2t minus e raised to minus t square by 2 into e raised to minus t, that is g of t. This is a method to find out the Laplace transform of a differential equation by partial fraction method, partial fraction expansion method. This you should remember. That is why I have given two different type of questions. How partial fraction expansion method can be used for a single or simple pole and third order pole systems. Okay. Next is application of Laplace transform to the solution of the linear ordinary differential equation. In this case, the system is represented by the differential equation, and you should find out the Laplace transform of the differential equation, and then you have to find out inverse Laplace transform so that you will get the solution. Okay, here there is a question. Consider the differential equation d square y of t divided by dt square plus 3 into dy of t divided by dt plus 2 into y of t equal to 5 into us of t, where us of t is unit step function. The initial conditions are y of 0 equal to minus 1, y dash of 0 is equal to dy of t divided by dt at t equal to 0 is equal to find y of t. You are asked to find out y of t. So to find out y of t, take Laplace transform of the differential equation. That is, Laplace transform of the differential equation will be equal to, first of all, Laplace transform of d square y of t divided by dt square, that is equal to s square into y of s minus s into y of 0 minus y dash of 0. Similarly, Laplace transform of 3 into dy of t divided by dt is 3 into s into y of s minus y of 0, plus Laplace transform of 2 into y of t will be equal to 2 into y of s, that is equal to 2 into y of s, that is equal to Laplace transform us of t, that is equal to 5 into us of t, that is equal to 5 into 1 by s. So we can write the equation as s square into y of s minus 5 minus 2 plus 3 into s into y of s minus 3 plus 3 plus 2 into y of s is equal to 5 by s. And then we can write the equation as s square into y of s plus 5 plus 1 into 3s y of s plus 2 y of s is equal to 5 by s. S square into y of s plus s square plus s plus 3 into s square into y of s plus 2s into y of s is equal to 5. Here the denominator of s from the right hand side of the equation is taken to left hand side. Next, s cube into y of s plus 3s square into y of s plus 2s into y of s is equal to 5 minus s minus s square. So y of s can be taken outside, so that we will get y of s is equal to minus s square minus s plus 5 divided by s into s square plus 3s plus 2. And y of s is equal to minus s square minus s plus 5 divided by s into s plus 1 into s plus 2. And in order to find out y of t, we have to take the partial fraction expansion method and find out the inverse Laplace transform. Okay. So here it consists of a first order pulses. So it is very easy to find out the partial fraction expansion, that is equal to y of s is equal to k0 by s plus k minus 1 by s plus 1 plus k minus 2 by s plus 2. So that y of s is equal to k0 will be equal to 5, k minus 1 equal to minus 5, and k minus 2 equal to 3. The procedure is same as we discussed before, and y of t can be L inverse of y of s, that is will be equal to 5 by 2 minus 5 into e raised to minus t plus 3 by 2 into e raised to minus 2t. These all are simple methods. You should write the equations step by step, then you will get the solution. Okay. This is all about the Laplace transform, review of Laplace transform. In the next section, we will discuss about the mathematical modeling of the control system. So today we discussed about the Laplace transform. So you should go through the sessions properly, and you should write the equations, and you should go through the Laplace transform basics, so that you can easily solve the differential equation. This is all about today's section. If you have any doubt in my classes, you can directly ask me. Through messages. Okay, in the next section we will meet with the modeling, mathematical modeling of control system. Okay then, bye.